Welcome to homework.
Okay, let's find out what the relationship between these molecules are. The first thing that I would notice is that this molecule on the right looks a lot like the one on the left, but as if it were flipped over. And what I mean by flipped over is imagine you had a playing card where you could see the back, and you had it laying on the table, and you flipped that over so that suddenly you could see the face on the card, right? Right. And that's what we've done here. We've taken this molecule and flipped it over in the same way that you flip a playing card over. So suddenly, this chlorine, which was going away from us, is coming towards us. The bromine, which was on the left and coming towards us, becomes on the right and is going away from us. Okay. So that's what I mean by flipped. And that's exactly what's happened here. Okay. So these are, in fact, the same molecule. Say that they are identical. Okay. Next, we have this molecule. And something we may notice is that immediately something pops out at us. Previously, the three chlorines were all on neighboring carbons. This time, there's a carbon in between, right? So if these cannot be stereoisomers or really anything like that, they can't be enantiomers, diastereomers, or meso. They can't be resonance structures, but they do contain the exact same number of atoms, right? All we've done is swap uh, chlorine and a carbon. And I missed a. Yeah. Okay, never mind. All we've done is what is going on? Okay, yeah. All we've done is move this chlorine one carbon over. So these become regioisomers, or as they're referred to here, constitutional isomers. Regioisomers are a type of constitutional isomer. It means that they have the same parts. Constitutional, not constitutional, constitutional isomers. They've got the same parts but connected differently. Okay. And finally, we have this molecule. Okay. All right. So what's going on here? Well, this is what's known as a Fisher projection, and typically, what is meant by a Fisher projection is the following: there's a central atom, and then we are looking at it in such a way that the substituents that are coming up and down are going away from us, and the substituents on the left and the right are coming towards us. Okay. So it's kind of like if we were, for example, uh, looking at the molecule from this point of view, so that the bromine, might be in our left hand and the hydrogen is in our right hand. That's often how it's, we think about holding on to it from the left and the right. And we're in the middle here, and we're holding it out in front of us, looking down at this carbon, such that the methyl is going away and the ethyl is going away. Okay. So can we grab this in a way that we would put the bromine in our right hand and the hydrogen in our left hand, and the methyl would be going away? And the answer is no. If I stood right here and with my left hand, or with my right hand, grabbed onto bromine, and with my left hand, I grabbed onto hydrogen, right? Then the methyl would be going away. And when I picked it up and looked at it, it would look something like this. And we notice that we've, to get the methyl up top and the ethyl on the bottom, we've had to put the bromine on the left and the hydrogen on the right. 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 So these are not the same molecule. They're not identical at the very least. And what's different is that we've swapped the position of the methyl and the ethyl. And when we do that and we have a stereocenter, that is the same as saying that we have enantiomers. Right. So these are the two molecules. We could say it's like this, or if we wanted, we could say it's the two molecules are like this. In either case, we've got enantiomers.